You know, from the smartphone in your pocket to the massive engines on a jet plane, our modern world is built on technologies we can't even see. Seriously, we're surrounded by these ultra-thin, super high-performance layers that make pretty much everything possible. But have you ever stopped to wonder, how are they even made?
Right. That question, it really gets to the heart of modern manufacturing. We're not just talking about building things on a small scale. We're talking about building things on an atomic scale. And the answer is this fascinating process that acts like a totally unseen architect in our world.
And that process is called Chemical Vapor Deposition, or CVD for short. It's the secret sauce, the unseen architect behind some of our most advanced materials. It's the method that lets us build materials with a mind-boggling level of precision, right down to the atom. Okay, so how does it work? Well, the simplest way to think about it is like steam condensing on a cold mirror after a hot shower. But imagine that instead of water vapor, you have this very specific, carefully chosen mix of chemicals floating around as a gas. And instead of just forming a drop of water, they react and build a brand new, perfectly solid layer on a surface, literally one atom at a time. This incredible level of precision is exactly why CVD is considered the absolute gold standard for creating high-performance coatings. We're not just painting a surface here, we're fundamentally changing it, building a new, perfectly formed layer right on top. Let's get just a little more technical for a second. With CVD, you take these chemical precursors, the raw building blocks, and you introduce them as a gas into a reaction chamber. These gases then react with each other and form a solid, super pure thin film on the surface of whatever object you put in there, which is called a substrate. I mean, think about that. It's chemistry happening in the air that precisely creates a solid layer on a surface. It's wild. And this whole thing is incredibly systematic. It's a highly controlled dance. It starts with prepping the surface, then you set up the chamber's temperature and pressure just right, and then you introduce the precursor gases. Those gases react, they land on the surface, and they start to build the film, layer by perfect layer, until the job is done. It's construction on a microscopic scale. So why go through all this trouble? Well, because the results are simply unmatched. CVD gives you these incredibly pure and high-performance films, and since it's a gas doing the coating, it can get into every nook and cranny, perfectly covering even the most complex, weirdly shaped objects, something other methods just can't do. The new layer isn't just sitting there either. It's chemically bonded to the surface, which makes it unbelievably durable. And its importance is all around us, I mean everywhere. The integrated circuits in your phone couldn't exist without CVD. The protective thermal coatings on jet engine turbines that keep them from melting, yep, that's CVD. The materials in our LEDs and solar cells, or these special biocompatible coatings on medical implants that stop our bodies from rejecting them, all of it, every single one, is made possible by chemical vapor deposition. But you knew there was a but, right? Of course, this level of perfection comes at a price. Achieving these amazing results creates some pretty significant challenges and trade-offs that have, for decades, kind of limited where and how it can be used. So here's the core trade-off in a nutshell. On one hand, you get that incredible quality and perfect uniformity. But on the other, it often requires crazy high temperatures. You get these tough, high-performance films, but the process can involve some pretty hazardous chemicals and really expensive, complex equipment. Let's break these limitations down real quick. First, the heat. Traditional CVD can require temperatures of over 1,000 degrees Celsius. That is hot enough to melt or completely wreck a lot of materials, like plastics or even some metals. So you just can't coat them. Simple as that. Second, the materials themselves. The precursor gases and what's left over after the reaction, they're often toxic, flammable, or corrosive. This means you need expensive safety protocols and super careful handling, which adds a ton of complexity and risk to the whole operation. And finally, there's the cost and the sheer logistics of it. CVD needs specialized, really expensive vacuum chambers and precise control systems. Plus, the size of what you can coat is limited by your chamber, and you often have to take things completely apart before you can even treat them. It's a whole thing. So the big question for scientists has been this: how do we get the perfection of CVD without paying such a high price in heat, safety, and cost? And this is where the story gets really, really cool. Innovation has been chipping away at these limits, leading to some incredibly clever evolutions of the original process.
Over the years, scientists have come up with several awesome variations. For instance, there's plasma-enhanced CVD, or PCVD. It uses an energized plasma to get the reactions going, which means you don't need nearly as much heat. That was a huge step forward, opening the door to coating heat-sensitive materials. Other methods, like atomic layer deposition, or ALD, focused on getting ultimate precision, giving us the ability to build films one single atomic layer at a time. Each innovation was designed to tackle a specific problem.
Now, a particularly exciting innovation is photo-initiated CVD, or PIC-CVD. As these researchers pointed out, this technique shows the potential to do what was once thought impossible, create these advanced coatings at normal everyday conditions and at a low cost, just by using light to kickstart the reaction.
And when you compare the old way to the new way, the difference is just stark. Traditional CVD needs intense heat. PICVD can run at room temperature. The old way needs expensive, specialized gear. The new way can use affordable, common UVC germicidal lamps, the kind used for sterilization. And instead of complex precursors, it can use simple gas mixtures like syngas. This is a fundamental shift in how accessible the technology is.
This really is a potential game changer. By using light to power the chemical reactions, PICVD makes the entire process so much simpler and cheaper. All of a sudden, creating these high-tech films doesn't require a massive, high-temperature factory. It opens up the world of advanced material science to way more researchers and industries than ever before. These innovations are paving the way for a future where we can engineer materials with this incredible, unprecedented control, unlocking technologies we're only just starting to dream up. The future, it seems, is very, very thin. So what's on the horizon? Well, researchers are using these advanced CVD techniques to create brand new 2D materials like graphene. They're integrating it with 3D printing to build complex, functional objects from the ground up, and they're developing sustainable, green processes that use less energy and safer, recyclable materials.